So today I'm going to be talking about cochlear implants, and I'm going to focus specifically on the critical period for language development and speech development after a congenitally deaf child gets a cochlear implant. So just to refresh, the book talks a little bit about this, but I want to give a little bit more context. So a cochlear implant is a biomedical device that is used to help correct sensorineural hearing loss. So as a refresher, sensorineural hearing loss is a type of hearing loss that's going to primarily affect the inner ear. And that's going to be things like the cochlea, their inner hair cells, anything that kind of helps receive a stimulus and transmit it to the brain in that electrical stimuli. And conductive hearing loss is a type of hearing loss that is instead going to focus more on the middle and the external ear. And so, because sensorineural hearing loss definitely can take effect at a range of different ages, the implants are performed at a variety of ages. So, you can get someone who has been able to hear pretty well for maybe 3, 4, 5 decades of their life, and then suddenly they have really profound sensorineural hearing loss. They might receive a CI. Alternatively, you might have children who were born deaf who have never received any auditory stimulus on their own, and they might be wonderful candidates for a CI. And that's sort of the angle that I'm going to talk about today in thinking about the development of neuroplasticity and various auditory circuitries and how that development influences the cochlear implant's functional outcome. So with that, I'm going to be primarily focusing on a possible critical period for speech and language development and how we can surgically operate and put a cochlear implant in at the best time in order to maximize that development eventually. And so, just as a refresher, cochlear implants work by having two pieces. So, there's an external microphone and a removable headpiece, and then the really important part for its function is this internal cochlear transmitter. And that's something that's going to go within the inner ear, and it's going to have electrode implants that attach to the cochlea, and it's going to really enable the cochlea to have a replication of the tonotopic maps and enable frequency coding as an ear would do in a healthy cochlea. And so, like I have written here, by implanting these electrodes, it allows the electrical device to mimic a tonotopic map, and that allows the signals to be transmitted to the brain as they would in a typical cochlea, and allows the brain to receive them in the way that it's programmed to do. And so, when thinking about cochlear implants and how they're being used in children who are born congenitally deaf, these children are often excellent candidates for cochlear implants, and that's because they're really quite young, and so they're still undergoing a lot of neuroplasticity. So you're looking at things like increased synaptogenesis, so many different synapses firing, active neuroplasticity circuits in early childhood as they begin to make all these neural connections. So at this point in time, the cortical function is going to be a lot more malleable than it would in a 40-year-old, a 50-year-old, 60-year-old, something like that, where their brains are pretty much fully developed. And they don't have a lot of those increased synaptogenesis pathways and connections happening. And so, as a child who was born deaf begins to develop, naturally they do have this auditory pathway programming in place. And the way that neurodevelopment works in children is that as a child receives a sensory input and it learns how to process it in the brain, then based on that, it's going to become better and more efficient about processing that in the future. And so a lot of people have heard, the phrase use it or lose it when it comes to a muscle and with working out, things like that. And that same principle is going to apply here as well. So if a child was born deaf and they have this auditory pathway system and programming all in place, but it's not used because the ear isn't receiving auditory signals, then over time, if that's not used, then the synaptic connections that built it up just won't exist anymore. And so that's when you're looking at things like synaptogenesis, myelination, synaptic pruning, all of those different processes coming into play to sort of make that pathway not quite as robust as it would be if it did receive active stimulation. And so then thinking about how that principle affects children who were born deaf and the fact that they don't necessarily receive sensory input through their auditory pathways, when you're looking at the possibility of a cochlear implant, you really want to try to maximize the functional outcome. And so with this, you want to implant the CI at a point in development where they still have these neuroplastic pathways in place, right? So they're activated, they're still able to make all these synaptic connections. The cortical function is pretty malleable at this point in time, but you're not at a place where their speech and language development is complete or ideally has even begun. Because then you can implant the CI, you can have the brain get used to receiving this auditory stimulus and have it integrate itself in the brain, and then once that is a lot more robust, then it can be integrated in the speech and language development and processing. And so with that in mind, I sought out to find a couple different papers that touched on this idea of a critical period of speech and language development, especially as it relates to the CI surgery in congenitally deaf children. And so something interesting that I found was the P1 CAEP biomarker. And this is essentially a measurement of the number of evoked action potentials on the primary auditory cortex, or P1. And so this is basically measuring the number of different sort of neural connections, firing rates, things like that, within auditory pathways and auditory processing. And so naturally, as a child ages and as they get into later childhood, because neuroplastic pathways are going to inevitably decrease, the CAEP is going to decrease as well. And so like I said, this is due to sort of this refinement of synaptic connections. The cortex is maturing, it's getting used to receiving the stimuli that it already has received, and it's going to start to prune away the ones that it hasn't. And so looking at this biomarker, researchers and scientists can get a pretty good idea of where an individual is at in terms of their development of P1 circuitry and just general auditory connections and connectability within the brain at that point in time. And so this biomarker is a pretty critical part in determining where this critical period lies within different children. And so this study by Sharma and Campbell that I looked at sort of examined this biomarker and saw how it related to when children of different ages receive the CI surgery. And so they found that there is a correlation between the biomarker levels and the surgical results. And so the CI surgery given to children under 4 years of age yielded the best speech and language outcomes many years later when speech and language development were commencing and continuing throughout. And alternatively, CI surgery done in children over 7 years of age yielded much worse outcomes. And then, because obviously development is quite variable within children, the surgery between 4 and 7 years of age yielded variable outcomes. And so something that's important to consider with this is that the critical period then lies somewhere between 3.5 years and 7 years for the best outcome in order for the child to have optimal language development. And this paper was pretty important in identifying the biomarker and tying it to that critical period so that physicians will have a better idea of what that period is for the child and what it is in general, which is 3.5 to 7 years.